Yeah, we are now at 3 o'clock. You're at what? 8 o'clock?
It's very civilized. No, 9 o'clock. It's
9 o'clock.
It's a good time. Yes.
Yeah. Yeah. We have some more people joining us, so we are okay.
That's good. Yeah, let's catch a few more people.
Yeah, we're catching up. Adding more and more people now.
Good.
Actually, my son is still in the UK right now.
Oh, where is he located?
Yeah, he is in London.
All right. Yeah, how's he getting on? All right with the pandemic? He's been
well. He got his first shot about 2 weeks ago.
Good. That's great. Yes. He's at university, is he?
No, he's been working for Bank of England. He's a PhD now.
Very good. Yes. Yeah.
He's been the analyst, senior analyst in the bank. So.
Wow. Yes.
Yeah.
Excellent.
It's been. Time is flying, and suddenly the kids are grown up.
Yes, that's right. Yes. Yeah, it's big changes. Yeah, that's very cool. Anyway, to be in the Bank of England, I think that's it's a good time to be in the whole sort of management consultant and analyst area. I think with all the data analytics and everything that we've got, it's great, fantastic. Oh, we should catch up afterwards. Yeah.
Yeah, sure.
Yeah.
Yeah. Adding more and more people now. Very quick.
Very good.
Yeah. So yeah, it's pity that traveling is really limited right now. So otherwise, you can be here in Jakarta too.
Yeah. Yes. No. I mean, it's been very strange not to be traveling. I think perhaps we have to look on the positive side that opportunities like this, we probably wouldn't have imagined doing this kind of thing 2 years ago, and yet it's perfectly feasible. We could have been doing this. We could have been having meetings and getting together in such a way. So this is a really good opportunity, and everybody's improved their communications capabilities, and this is a real privilege for us all to have the chance to get together like this, I think.
Yeah. Right, perhaps we have like more than 50 people right now, so perhaps we can start. So welcome to online technical group discussion of NACE in International Indonesia. This is one of the events that we have besides Bintaro. It's called Bincang-Bincang Santai Korosi in Bahasa Indonesia. And we also have another program called Corrosion Discussion Podcast. And I'm here hosting this discussion together with Andri Sutiawan. He's a prominent young engineer. Hi, Andri.
Hello, Pak Kuku. Hello, Dr. Liane.
Hello.
I'm pronouncing it correct?
That's great. Andri.
Right.
Good that you could join us today. Fantastic.
Yes. Thank you. So thank you very much for your sparing the time to share some of your knowledge to many of us in here. And we also like to welcome everyone, ladies and gentlemen. Thank you for joining our event from wherever you are.
Yeah, thanks, Andri. In this occasion, Andri will select and read your question in the Q&A session. And we are very fortunate that we could have Dr. Liane Smith as our guest this time. Good morning to you again, Dr. Liane.
Good morning, everybody.
Yeah, well, I know her since late 90s, actually, when she presented nickel-based alloy in Jakarta. And personally, I met her in early 2000 in the UK during my assignment, a well-known expert in corrosion engineering. And in this occasion, she will share her expertise in CO2 corrosion modeling. So it's not surprising that we have so many participants. We have about 220 registered participants. It's one of largest number that we have. Besides, well, in our podcast we have sometimes in this number as well. So before we move on, I would like to address some the housekeeping rules. Andre, would you please show us the housekeeping rules? Or perhaps we go to the agenda first. Yeah, we have introduction. We did that. We will have a safety moment, and then we will have opening from Pak Rizal as NACE chairman, and then the presentation itself and closing. Okay, Andre, make it we go to the housekeeping.
Okay, thank you, Pak Kuku. Yeah. So to make the event comfortable to everyone, please follow some general housekeeping rules. So the first thing is, by continuing with this event, participants are automatically giving consent to be recorded. We will record the event. And for all participants, please disable microphone and camera during the presentation to ensure smooth connection and minimize stress to overall internet bandwidth. Especially right now in Jakarta, it's raining pretty hard, so there might be some connection problem. We expect some connection problem. So let's see. I hope everything will go smooth. And for the third one, please put questions in the chat box. Host, me and Pak Kuku, and my team from NACE Indonesia section will post. We will select and read some of the questions during Q&A session. And when there is technical issue during presentation, please write in the chat box. Some of our team will try to help you. And this is important. This event will take approximately 2 hours. So please relax, and we encourage you to prepare some coffee, tea, or some snacks so that you can fully enjoy the experience of the presentation. And last thing, we hope that all participants can get many positive things after this presentation for the takeaway. Back to you, Pak Kuku. Or
yeah.
Go directly to...
Okay, probably we can go to the safety moment, Andre.
Okay, safety moment. This is a reminder for us. Let me check my screen for a while. So these past few weeks, we have seen in the news many fires happen in some refineries and chemical plants. So we hope these safety moments will be a good reminder to ensure equipment integrity from our side as corrosion professionals. And let's see, it's a short presentation.
April 2nd, 2010, the Tesoro Refinery in Anacortes, Washington. A nearly 40-year-old heat exchanger violently ruptures, causing an explosion and fire that kills 7 workers, the largest loss of life at a U.S. refinery since 2005. The Chemical Safety Board launched an investigation and determined that the heat exchanger catastrophically failed due to long-term damage from what is known as high-temperature hydrogen attack. The Tesoro Refinery in Anacortes is an 800-acre facility located approximately 70 miles northwest of Seattle. The refinery produces a variety of products, including gasoline, diesel, jet fuel, and asphalt. Within the refinery's naphtha hydrotreater unit, raw naphtha, a light component of crude oil, is treated to remove nitrogen, sulfur, and oxygen impurities. Before entering the unit's reactor, the raw naphtha and hydrogen are preheated inside pressure vessels called heat exchangers. The unit contains 2 banks of 3 heat exchangers supported by a 3-level steel structure. Each heat exchanger consists of a bundle of tubes inside a steel shell. Hot fluid exiting the reactor flows through the heat exchanger shell, while cool fluid headed for the reactor flows inside the tubes. Heat is exchanged through the walls of the tubes. Every 6 months, the heat exchangers are taken offline to be cleaned because of fouling, a common occurrence when operating heat exchangers in this type of service. As the raw naphtha is heated, a scale-like material forms and deposits onto the inside of the tubes, hindering the transfer of heat in the exchangers. On March 28, 2010, 1 bank of heat exchangers was taken offline and disassembled for cleaning, while the other bank remained in service. This allowed the unit to continue to operate. By mid-afternoon on April 1st, the cleaning was complete, and operators initiated the startup of the offline bank of heat exchangers. The procedure required an inside board operator monitoring the control console and 1 outside operator opening and closing large manually operated valves. But the heat exchangers had a history of developing leaks during startup, something that refinery personnel had come to see as normal. Additional operators from other nearby units were called upon to assist with the startup, including mitigation of potential leaks. By 10:30 p.m., the outside operator was joined by 6 workers from other units within the refinery. The 7 workers were located around the heat exchangers, where startup activities continued past midnight. But unknown to the workers, the steel shells of the middle vessels in both banks of heat exchangers had been severely weakened due to cracking caused by high-temperature hydrogen attack. This occurs when tiny hydrogen atoms diffuse into steel at a high temperature, then react with carbon in the steel to form methane gas. The larger methane molecules, unable to diffuse out of the steel, accumulate, stressing the steel and over time causing fissures. In both of the middle heat exchangers, the fissures grew and connected to form large internal cracks. One such crack was 48 inches long and extended more than 1/3 of the way through the vessel's 1-inch thick shell. Shortly after midnight, the temperature of the fluid exiting the tubes of the online bank of exchangers increased about 75 degrees over the span of 3 minutes, a temperature increase that was typical and observed in previous startups. But the middle heat exchanger was so severely weakened from high-temperature hydrogen attack that it likely could not withstand the stress caused by the rapid temperature increase. At 12:35 a.m., employees working at a nearby process unit heard a loud hissing noise when vapor began to leak as the heat exchanger cracked at its weakest point. Seconds later, the exchanger violently ruptured. Hot hydrogen and naphtha vapor rapidly vented from the exchanger and spontaneously ignited upon contact with air, resulting in a massive fire that consumed the heat exchanger structure. 3 of the 7 operators died at the scene. The other 4 operators were transported to local burn centers with severe injuries. 2 died within hours. The other 2 succumbed within days.
Okay. Thank you, Andre. Welcome back. Yeah, for the next is for Pak Rizal, as NACE International Indonesia Chairman, to address his remark for this event. Please, Pak Rizal, it's yours now.
Yes, thank you, Pak Kuku and Pak Andri. Good morning to you, Dr. Liane Smith from London, and then good afternoon to all of the attendants. I would like to say thank you very much to Dr. Liane, who willing to spend the time to share your knowledge and experience to the NACE Indonesia section, and then to the Indonesian corrosionist and then the corrosion practitioner in Indonesia. I'm really appreciate for this. So NACE Indonesia section was gather the expert in Indonesia on corrosion field by some activities such technical discussion groups, corrosion talk, as Pak Kuku mentioned earlier, that we call it as a bincang santai korosi in bahasa, meaning to say that this is the corrosion talk, and then also the corrosion podcast. So far, the response was very good with plenty attendance and then the interactive session. Normally, the presenter or expert is the volunteer among us. It was meaningful session belong to us. But today, we got a very special presenter. We are happy to get Dr. Liane today. Thank you very much for your willingness and coming to this room. So, as we aware that carbon dioxide corrosion is the major problem of corrosion in oil and gas production, is particularly found in the oil production material as tubing, casing, are more exposed to the carbon dioxide pressure environment in the deep water environment. So this session is valuable even for the community. Hopefully we will get many insights to the attendance. Again, thank you very much to Dr. Liane for your coming to this room and then for your willingness to share the experience. And finally, let's enjoy the session. Thank you very much. Good afternoon. Sorry, yeah. Thank you.
Thank you, Pak Rizal.
Thank you, Pak Rizal. Just a reminder, sorry, to all participants, before we start, can all the participants please fill in attendance form with link in the chat box? And there is an important option in the form for you to get more detail about Larton. So please fill it in, and if you want to get more information about Larton, please click the tick the checkbox. So, and we will come back to you to give more information. If you have questions, also you can put it there. Okay, Pak Kuku.
Yeah.
Back to you.
Thanks. Yeah. Thanks, Andre, and also thank you for your encouraging remarks, Pak Rizal. Then I would like to read Dr. Liane Smith bio. Dr. Liane Smith is an international renowned engineer and entrepreneur. Her work experience in corrosion and materials engineering covers 40 years, working globally, mostly in the upstream oil and gas sector. She spent 10 years with the Shell Group, over 20 years running her own business in the Tech Ltd, and 5 years with Wood Group. In 2018, she formed her new venture, Larton Ltd, consulting engineers. Liane was awarded a fellowship of NACE in 2009 for her work related to modeling of corrosion and materials selection. And in 2011, she was made a fellow of the prestigious UK Royal Academy of Engineers. And now, I will leave the presentation to Dr. Liane Smith. Liane.
Excellent.
Yes.
Thank you very much indeed. Well, I'm going to first of all just get through the mechanics of sharing my screen and getting up my presentation. Just one moment, please. There we are. And let's get this clear from the beginning. Very good. Okay, so it's my enormous pleasure to be here today to have this opportunity to speak to you all, and I'm very honoured that you have all given up some time to join us for this meeting. It's a wonderful opportunity. I'm going to be also here joined by my partner in the business, Dr. Mike Billingham. Mike is a great corrosion expert and also has enormous expertise in steel and steel products production and sour service. And also we are joined by Mrs. Melissa Jean, who is with our partner in Indonesia, PT Energy Partners. And please also bear in mind you can address questions afterwards if needed to her directly, and she will make sure that those also come through to us. But let's focus on the technology, which is why we've all come together today. So I'm going to be talking about a history and overview of CO2 corrosion modelling, and I've responded to topics that were proposed by yourselves. I'm aware that these topics are things that are areas of strong interest to some of you, and perhaps some of you are studying this area and do know quite a lot about the topic. And then for others, it's a matter of just general knowledge and general learning that you've joined us today. So I've tried to pitch the talk at a level where we are talking about things. I hope that people will learn something new by joining this today. But if there are any points that you want clarification on, you can pop them in the chat box, and we'll try to pick up the clarification points as we go along, sort of short things that just don't make sense to you. But if you need more help afterwards, don't hesitate to get in touch, because if there are things where I didn't make sense, I'd much rather have the ongoing conversation with you and help you along than leave you wondering what on earth I was talking about. So I'm going to cover this in groups, and the first 4 topics will come together, starting with the first 2, and then we'll be taking a break after the first 4 topics for questions, which will be in about half an hour's time. So let's get started and say, well, we're talking about CO2 corrosion, we're talking about internal corrosion. So what is the corrosion rate? That's pretty easy, isn't it? We all think we know that we just got to find the difference between how much steel we had at the start, how much steel we got now, and what's the time difference between them. So if it's that easy, what's the problem really? Now the thing is that neither of these things have single numbers. The original wall thickness is not a single number. Steel is not uniform. To give you an example, this data is the axis at the bottom is the thickness of steel in millimeters, and it's a frequency distribution. So what we've got is the number of incidences on the vertical axis. So what you can see with the orange graph is that steel, when you buy it, has a certain distribution of size of the wall thickness, and this sample is real data. It comes from several, a couple of hundred readings taken from some actual pipe, and the orange represents the, let's say, the uncorroded wall thickness of this piece of pipe, which is plate steel. It's rolled steel. Now, I can assure you that some products will be very much broader distributions. So what is the actual original wall thickness? It looks like it should be 20.5, but I can tell you that the actual specified wall thickness in this case was 20.6. Well, more than 80% of the data falls below the specified wall thickness here. And if we look at the blue curve is about 300 data points measured circumferentially around a pipe that has been corroding for about 3 years. We've got similar data for a number of locations, and it's basically just inspection data, but it's probably more detailed than we normally get hold of, because it was very strictly taken every few millimeters around the pipe. They took wall thickness reading with ultrasonic inspection, so it's pretty accurate. And even so, what we see is that there's a broadening of the variation of the width, and there's quite some question mark about, well, actually, what represents the real thickness of this pipe? So if you think about it, the difference between the original wall thickness and the current wall thickness could be almost any number you choose, depending what number you pick for your original wall and what number you pick thickness. We normally work from the nominal. If you think about risk-based inspection or something, you say, well, what was it originally? It's the nominal wall thickness. But the tolerance is up to minus 12.5% of the wall thickness in some specifications, and things like fittings can be very variable in wall thickness. So it can be actually quite a lot thicker on one side and thinner on the other side. So that's something to keep in your mind. And the inspected wall thickness is not necessarily the thinnest location. You think you've taken the thinnest place and so forth, but even the best of inspection methods are only sampling. So even a 40-finger caliper tool, as I'm showing on the left, which can be pulled through tubing, will actually only be sampling maybe up to about 10% of the area of the pipe. So when people say to me, does modelling work? Does it represent the real life? The answer is, well, we don't actually even know what real life is. So it's just to keep in mind that we do our very best, but corrosion engineering is a complex science, and there are difficulties with it. With CO2 corrosion modelling, CO2 corrosion has a very particular appearance, and it distinguishes quite, you get used to looking at it, you understand that it's different from, say, oxygen corrosion or acid corrosion, because you have these areas which appear to be unattacked. You've got flattened areas, you can see them on the left sample here, and then you've got deeper areas which are all remarkably uniform actually in the depth. They all corrode down to around the same depth. And this is what we call mesocorrosion. It's a term that got established for this type of corrosion. And I call it generalized attack. There's a lot of discussion as to whether you're talking about localized or generalized. And the reason I say it's generalized is because if I took an inspection of part of this piping, it doesn't really matter if I looked here or I looked here or wherever, I'd probably get a similar kind of impression of the corrosion. Whereas if you've got localized attack, and I think particularly say of microbial influenced corrosion or pitting type corrosion, it really is localized, and there may be no attack whatsoever elsewhere, and you've got to be very lucky to find pitting corrosion through just general inspection. So what we're trying to model is the rate of attack at the bottom of these mesas. So really, how deep are we going through the steel in the areas that are not protected? In the early 1980s. I began work with Shell in 1981, and he was at the time working with me in the Netherlands, and we had the problem of CO2 corrosion arising in what was called the Groningen gas field, the largest gas field in Europe. It had about 0.7 bar of CO2, and at the typical temperatures of 40 to 50 in the field, we were getting corrosion rates of about 0.7 millimeters a year. And you can see that if you could move this line on this nomogram and you could link up 0.7 and about 50 degrees, you'd go through around about 0.7 on the corrosion rate chart. So this is an illustration that's important, that when people do work on corrosion, they're working normally for a system. They're trying to explain something. And CO2 started with that gas field and trying to understand that gas field. And then what happened, of course, is that people started to say, well, we've got CO2 corrosion elsewhere. We've got CO2 corrosion in other parts of the world. We want to use this tool. And it's a question about how widely can you stretch the use of a tool like that. Now, many corrosion models have been developed from this. This original research done by Shell in Amsterdam was expanded by a lot of work in the Norwegian lab, IFE, and over time additional factors were taken into consideration. But this is where it all began. Now, where are we with modelling nowadays? And I'm going to outline three broad approaches. We've got an empirical approach, we've got semi-empirical, and we've got a mechanistic approach. Now, some people think that machine learning and AI and everything like that is new. I can tell you that in the mid-80s, Case Tavard and I were having discussions about should we be looking at neural nets was the big topic to discuss. We thought a lot about it, but what was apparent was that it's even more focused, because when you build up a knowledge base that these systems can work in, you have to have a set of data. You need an awfully large amount of good quality input data. Normally you need a training set of data that you use to set things up, to build your artificial intelligence and write your algorithm, and then you test it against other things. It's very difficult to give that system validity beyond where it started, just as much as the original nomogram, to be fair. But I can say that at the moment, success has not been great with CO2 corrosion. There could be other areas where this does have success, and we now have such better computing power that there could be opportunities in the future, and we can come back to that at the end. The semi-empirical approach is a mixture of physical models and data fitting, and what we're trying to do is understand the data, and we're not trying to model all the mechanisms in detail. It comes from laboratory data and field data, and it's the basis of practical corrosion prediction models that are out there mostly in the market now, and I name a few here. They're all developed from the original Devard CO2 corrosion equations, and improve on it and grow on that, and have expertise built in from the different people who've developed these models. Finally, the mechanistic model is really focused on the chemistry and understanding what steps are taking place, where are the cathodic and anodic reactions going, what's happening to the protons and so forth. And if we could really truly understand all that, then the thought is that this would be the most correct approach, and it would be more accurate and widely applicable. But in practice, there's been an awful lot of very good work done by workers in particularly the Ohio University in the United States. But when they make major steps forward in understanding, their change in understanding means that they almost have to put to one side a lot of the work they've previously done and start again. It's very challenging. What I would say is that the work they've done has really opened our eyes and given us a lot of insight to other things and helped to improve many of the semi-empirical models. So going to the semi-empirical, which is where we are talking today, if you look in the internet papers, you'll find this basic resistance model. It says that there's an activation energy. If the activation energy is low, so that we've got a fast reaction process, then we're limited in how fast the corrosion rate goes by how fast we can actually deliver corrosive species to the steel surface, and vice versa. If the flow is very restricted, then the rate of corrosion is determined by how fast the reagents can actually react at the steel surface. Now, as you'll see, there are not many parameters here. There's very few things in those two equations. There's just these 5 items listed on the left here. So if there's so few factors, why is it so difficult to model? And the issue is that each of these factors are actually influenced by an awful lot of other factors. So when we actually want to take those 5 inputs into the equations, we've actually got to gather an awful lot of other data. We've got to get hold of detailed information in other areas. So in fact, the list of inputs that we have to our corrosion models is more like 15 parameters rather than 5 because of everything else that we need. And we need to manipulate that data and generate some of the inputs that we're seeking. Then beyond that basic V-core equation, we have other adjustments to tune the CO2 corrosion rate, and these are including whether or not we're getting oil wetting or scaling and other factors that are altering the environment and changing the corrosivity. So we end up with our equation, which is that the corrosion rate we're trying to model is our theoretical V-core rate multiplied by a number of factors. We can call them fudge factors. They are adjustment factors, bearing in mind that our environment has some special conditions that alter the corrosion rate. And these have been fantastic in giving us a capability to tune field data to give us a better match between what we're measuring and what we're modeling. Now, I'm going to look into one of the areas in a bit more detail, which is flow modelling, because this is a very important topic. So what we have on the right here is a flow pattern map, and there are a number of these available. This is published by Petalas, and it is one of a whole suite of flow regime maps that he gives for horizontal flow, vertical flow in a variety of different conditions. We've got different kinds of flow, and here we're thinking about multi-phase flow where we've got gases and liquids flowing, and when we have these different flow regimes, some of them are what we'd say are symmetrical and some are not symmetrical. So annular flow, slug flow and so forth, these are flows where the same environment is effectively passing the steel along all surfaces of the pipe. But a stratified flow will give us a separate gas cap and a lower liquid cap, a liquid layer, and that is where we can start to see top of the line corrosion, oil and water separation, etc. Now, there are specialist modelling systems out there by a number of companies that give us insight into this flow modelling, and these are extremely valuable to really understand. If you're going to spend millions of pounds on a pipeline, then probably you are going to get a full hydrodynamic study of it, and the data from that can be very helpful to input into our understanding of how to corrosion manage the pipeline. But that's kind of software is geared at understanding pipeline sizing, pipeline flows and so forth, pumping demands and all that kind of stuff. It's not particularly geared at corrosion modelling. What we also want to be able to do is get some modelling with a limited number of inputs. We want to have a corrosion calculation that we can reasonably run and get an answer within a matter of a minute or so, rather than a really extensive computation. What we feel is that you need to take into account that you don't have ideal behaviour in gases. That's one important thing, particularly at very high pressures. We definitely need to take into account the tubing deviation or pipeline elevation, because the angle of flow of fluids is important. And in wells, we have the injection of gas at certain depths or the injection of water in some kinds of secondary recovery, and those need to be considered. So all of these things need to be considered in the modelling, which make it a practical model, and these are not readily incorporated within simple flow modelling systems. Now, what happens when we look at a pipeline elevation, as you see on the right here? This is a typical pipeline that's running along the seabed, and then it's coming in on a shore approach coming up to the landfall here. So it's about 70 meters deep at the deepest. And we see a variation in flow regime, areas that are stratified, some upward going areas that are annular, and some areas going up that are bubble and slug flow, flowing from left to right in this diagram here. At these different areas, we'll have areas where perhaps we can't guarantee that corrosion inhibitor will be spread to the top of the line. We can't guarantee that we'll be able to protect this line. And it immediately tells us how we're going to have to adjust our corrosion management to include pigging to push fluids through and things like that. The varying flow velocity will affect the bottom line corrosion rate. And related to this, we have the question of water separation. Oil and water is flowing along the bottom of the pipeline, and it will be carrying the water in an emulsion, which is actually completely contained. If you look at the structure of an emulsion, as long as the water is inside the oil, it's surrounded by oil particles, molecules, and these are protecting the water from actually impinging on the steel surface. But when we have stratified flow, we have slow-moving, possibly stagnant conditions. It can take days for a molecule of water to get from one end of a pipeline to another. It's held up at various places, and in those conditions we can get water separation. So we have an oil wetting factor, which is determined from this equation, and we have within that a water break element, which is related to the API gravity. Now this part of the factors affecting corrosion was determined from real field studies actually carried out by myself and other workers in our business at a certain point in time. It was published data, and it's been picked up by many of the public models, but not all of them. And we think this is one of the key factors that helps to explain why we get certain behavior in the oil business. That question of water dropout is also affected by pipe diameter. On the left, we've got a classic example of a line carrying oil, and you can see the groove in the bottom of the line that's been caused by the water dropping out. Because notwithstanding the previous equation I showed you, fundamentally there's a certain velocity at which even the smallest amount of water will eventually separate out from an emulsion. And this in the typical diameters that we're mostly dealing with, around 0.2 to 0.3 of a metre, we're about 1 metre a second, but there is a variation with pipe diameter about this dropout velocity. But what we often see is that people oversize pipelines. It's a general trend of pipeline designers, and I always stress to people that if you don't get the velocities right, the risk of actually having a long distance separator between your fluids in and your fluids out is very high, and we see a distressing amount of damage on oil pipelines due to this problem. I'm moving on now to the second two topics, scaling and inhibition and pitting. The first one is the bicarbonate scaling, and part of this is those mesas, that the surface that's not attacked is generally covered with a bicarbonate film. As the temperature increases, that iron bicarbonate becomes increasingly protective and adheres increasingly strongly to the surface. And we have therefore to consider that the temperature, whilst it normally increases with increasing temperature, it reaches a point at which the protectiveness of the scale starts to counteract that, and we get a drop-off of corrosion rate. And so we have this scaling effect, which is derived both from laboratory experiments and also from observations in the field. And the actual scaling temperature is not always the same temperature, but typically around between about 55 and 75 degrees C, we start to see this drop off. So typically in a well, you have higher bottom hole temperatures, and the temperature drops as we come to the surface of the tubing. And the corrosion rate very often follows this pattern, where we've got a higher corrosion rate going to a point, and then scaling kicks in more strongly, and we get this drop off of corrosion rate. So the thing to be aware of here is that the corrosion that you measure at the highest temperature, don't assume that's going to be the highest corrosion you'll ever see in the system. It could be at an intermediate temperature from this, because of this problem. Now moving on to sulfide scaling. Hydrogen sulfide is found in many parts of the world in the reservoir fluids, and it also comes into aging reservoirs as a consequence of the seawater injection that we do over time. So even fields that you've known as what we call sweet, CO2 only fields, can eventually get H2S in them. It's a weak acid. It dissolves and reacts with the ions in solution, removing them as iron sulfide, which tends to deposit on the surface as a fairly adherent film. But the drop in pH that we see when we add H2S, if you have just a few ppm, you'll see that can actually cause a small increase in corrosion rate. But generally, once you get to tens of ppm or mole percents, then you normally see a real high drop-off of the filming rate. Now, it's been very difficult to get modelling of this from any kind of laboratory experiment, because all you measure in laboratories is a real low corrosion rate. It's hard to get anything really practical from it. What we do know is that from experience, if you're in very sour conditions where you've got a higher amount of H2S to CO2, so you're sort of in this area of this graph, then the hydrogen sulfide does not affect your CO2 corrosion rate very much. And so I beg your pardon, where you've got a high CO2, which is at the top end of this graph on the right-hand side, you don't have much reduction, so your H2S factor is a high number, so it's not reducing your V core value very much. But as you get increasing amount of H2S, then you get down to the bottom here and you'll get a real drop down of your corrosion rate. The blue line is the Larkton software model that we've fitted to this data that we have. There are two other models that we're aware of out there, and one of them is tending to give, we think, overconfident reduction. We think that this, the corrosion rates are actually a little higher than this is giving, and another model is rather too conservative and is not really taking proper benefit of what we see, and we do a lot of work with sour surface, so we have confidence in this. Try to remember these facts about the pH, because I'll come back to that in a moment. I don't want to spend long on this. This is a Pourbaix diagram for the iron sulfide system, and just to say that there are many forms of iron sulfide and they are non-stoichiometric. That means they're not perfect, the ratios of iron and sulfur, and they're not terrifically stable molecules. You get shifts between them, and their stability varies with pH as well, and temperature has a factor, and also chloride content as a factor. Many people have studied this, particularly ExxonMobil have a number of key presentations and papers on it, and Total as well. And so these help us to understand why we get instabilities, why a sulfide film, whilst it's a wonderful thing, can be destabilized in certain conditions, and that's when we get localized pitting. When we get pitting, we break through that sulfide film, and the corrosion rates we've seen are comparable to the CO2 corrosion rate. Quickly moving on, the top of the line corrosion in sweet systems has been extensively studied, and it's shown that the top of the line corrosion rate is related to how fast we've got condensation taking place and what the solubility of iron is. So if we've got fast cooling rate, then we get a high condensation rate and a high top line corrosion rate. But as the iron concentration builds up, the iron solubility drops, and so the corrosion rate drops off. And we've got modelling related to this, and this is a pretty reliable model for sweet corrosion and has been used in many of the models globally. I want to point out there's an area where we really don't know too much at all, and that's top-line corrosion in sour systems. Now, this paper by Svenningsson in 2015 is a key reference to bear in mind for this. He's done laboratory studies. What we need to mention is that they're all rather short term, and there have been small test areas in these cases. But the kind of effects that he's showing is that corrosion rates are surprisingly higher at lower temperatures. As you see on the right here, the water condensation rates don't particularly affect the results, but you tend to get even less corrosion if there's high water condensation. And there's some impact of acetic acid, which is presumably affecting the pH. So there are some strange effects here, but just look at the kind of top line corrosion rates we're getting. These are quite serious corrosion rates, you know, plus or minus 0.4 millimeters. And he also publishes this data table, and these are the top of the line corrosion rates highlighted here, and you see that in the field we are seeing corrosion rates like this. Mike and I have currently been looking at a case with top of the line corrosion rates in a sour pipeline of about 0.7 millimeters a year. Very serious corrosion rates, very difficult to control, because also these don't arise at the start of the pipelines particularly. They can arise some distance along the pipeline. So it's rather different to sweet corrosion and very, very challenging indeed. So this is an area where there's further work needed. There's no predictive model for this at the moment. We feel that the issue could be related to the pH effect and the fact that ions are removed so easily from solution by H2S. And we think that the relative stability of this product FES compared to the iron carbonate means that you don't get that build-up of ions that you do in the pH conditions at the top of the line. So in sweet corrosion, you basically reduce the solubility of your iron over time, but that may not be happening in the sour system. Plenty of room for research for those of you who are in an academic field at the moment. Finally, inhibitors, fairly well established that the effectiveness of an inhibitor is the efficiency, which is normally extremely good because that's just on good chemistry. Get the right molecule and you've got a high efficiency. The availability is the inhibitor actually at the surface of your steel, and that depends upon the engineering system you've put in place, whether you're batching, whether you've got a good distribution of the inhibitor, and you need to measure the residuals to confirm that you've got good a good covering of the surface by the inhibitor. We talked about flow regime, and different software systems use different approaches. I'm going to pause for questions and answers and see if there's anybody who wants to raise anything at this point in time.
Okay, thank you very much, Dr. Liane, for the first session. So there is a question from Suryani. So she asks about, for the scaling formation, is there any limit of upper temperature in which the corrosion rate increase again?
No, that's not been observed. The iron carbonate, the thermodynamics tell you that the iron carbonate is very stable as the temperature increases, and it doesn't go through an inversion and start to dissolve again.
I see. Thank you, thank you. So in the chat box, only question from Bu Suryani, but there are some preliminary question from participants during the registration, so I will ask about it as well. I think it's related to modeling. Earlier you said about modeling. What is the main difference of corrosion modeling for downhole, pipeline, and piping?
So the key thing here is that all of those systems are different flow regime systems. Tubing, production tubing is basically vertical tubing, and so we're interested in vertical flow, and the pipeline is horizontal, and obviously the pipe work is going in all sorts of directions. We never really know what the layout of piping will be. So the key thing is to understand, for tubing and pipelines particularly, make sure you understand the deviation profile or the elevation profile for the pipeline. But the model itself is robust for all of these areas. So it's a generic model that will cover from the bottom of the hole right through to the outlet of the pipeline. Indeed, it can be used in the correct areas of downstream systems like refineries as well. So the modelling is the same, but you will find a huge impact of flow is important to consider.
Okay, thank you, doctor. Good to know that. Another question from Rehan Ahmed. He's asking in the chat box. For sweet top-of-line corrosion, how effective have VCI? I assume this is vapor corrosion inhibitor result been so far. In his place in Petronas, he started a research project with the University Technology Petronas as a joint industry project. And if you can have advice on the successful of or effectiveness of VCI, please, do you have any experience about that for top-of-line corrosion?
I haven't got specific data where we know that VCI has been applied. I think the important thing is that corrosion inhibitors, the chemists and the expertise there is improving enormously, and the key question is whether they've got it right. If the inhibitor is one which will enter the vapor phase and dissolve in the top of the line, it ought to work. The answer is no. I haven't got specific experience that would say that that's going to be the answer. With sweet top of the line, the problem is very much at the start of the line, and so I would have hope that if we're injecting VCI at the start, that it would be effective. Generally, we only have to protect the first 5 kilometers or so of the pipeline, and that's to be hoped that we can manage that in a gas pipeline.
Okay, thank you. I hope it's answered your question, Rehan.
Yeah, you have one more question to run, Andre.
Okay, I think this is important from Asif. The last question for this session. The application of pipeline corrosion modeling for piping. It's an incorrect approach. So what is the right approach for this piping in the plant?
Oh, for piping. Well, if you can stay with the to the demonstration, I'll show you how we do piping. Basically, you have a very simple system that we can apply, which is in the Larkton. It's much easier to use than using a pipeline approach. And you're quite right. It's an area that corrosion models need to respond to, and we think we have done. So I will come back to that if I can.
Okay,
if
great. So
good.
People, please stay. So the
please
good
stay.
things will come. The good things will come later. So please stay, and we will continue the presentation, Doctor.
Thank you.
Don't touch the button.
Yeah.
Please go ahead.
Okay, so I'm going to move on now. I'm going to briefly touch on material selection modeling and then go on to this group of topics in blue, and then we'll take some more questions at the end of this section before we have the demo. So the modeling of the performance of materials, what we are aware of is that stainless steels have different levels of success in the CO2 and H2S conditions. Even in sweet conditions, materials like 22 chrome, 13 chrome materials, which are very widely and successfully used, they do have their limits related to, as you see on the left here, the chloride concentration, CO2 and temperature limits. Now, these diagrams I'm quoting here are from a Nickel Institute publication I produced with Dr. Bruce Craig, and it was updated in 2011, and basically these are saying that if the temperature exceeds the upper surface of these 3D contour diagrams, then you'll start to get a breakdown in passivity. So we rely upon the chrome oxide film on the surface, but that film is affected at temperatures, certain temperature conditions. What we also know is that there is a pH at which the passivity is broken down, and with some oil conditions we can definitely get below the passivity stability pH, and that can cause pitting. We also have the risk of cracking with some of these materials in sour service, and we can turn here to the ISO 15156 standard for a lot of guidance, and it has various limits in it. But also, again, there are other sources we can go to get information. And what you see here, for instance, is that pH limit showing here of about 3.5, which is a barrier between cracking and not cracking of 13 chrome in sour service. But in fact, at a pH below 4, 13 chrome will already have depassivated and started to pit. So there are other limits that affect the performance of materials, and we need to take a holistic approach of all these different mechanisms. So there are also these diagrams for different nickel alloys, taking into account the effect of hydrogen sulfide on their stability and usefulness and so forth. And all of these diagrams are incorporated into software like the ECE and also Larkton CM software for material selection. So now the question is, how do we translate all of this wonderful laboratory data, field data as well, specification data and so forth? How do we get that across to people? So in the ECE, the familiar approach was to allow people to put in a set of test data on the left-hand side and get traffic light results on the right-hand side. This is showing a tab for ISO 15156 data. Is the material allowed or not allowed in that standard? The ECE evaluation rules were following a set of rules about that I've just been illustrating to you. In Larkton CM, you have your input values to put in, and you can have multiple streams to analyze at the same time. And when you analyze these, you'll get a list of materials and then two indicators. One is whether the material is allowed or not allowed in the ISO standard, and on the other hand, whether it is a low, medium or high risk. So let me just remind you that in both ECE and Larkton CM, the approach is that the ISO standard is there only to give you guidance about cracking in sour surface, sulfide stress corrosion cracking only, whereas the risk evaluation is saying that these materials might suffer general corrosion, pitting corrosion, chloride stress corrosion cracking internally and so forth. And so for the different conditions that we've considered here, which are all varying sets of conditions, we've got different advice, and sometimes the ISO standard is saying there's a problem, and we're saying yes, there's a high risk associated with those conditions. But in some cases we're saying our experience shows us that these kind of materials will work perfectly well in the conditions you've got, despite the advice in the ISO standard. So in some cases we will go ahead with the use of certain materials where ISO is a required standard, then you have to follow its requirements for materials. I'm looking now at the other topics. I was asked to discuss the battery limits. We talked about the fact that these models are suitable from the bottom hole right through pipelines, and they're pretty generic models, but they are mostly focused at sort of the mid-round of ground of conditions, because that's where we've got lab data or field data. Different models have a different capability to model practical conditions. Some of them are better at handling the elevation profile of pipelines, or actually looking at the wells and looking at bubble point, the impact of a secondary recovery and that sort of thing. These are not very well covered by the majority of software. And they also tend to be limited in the high pressures and high temperatures you can go to. And you have to bear in mind that we depend upon physical and chemical constants in various places, and they're just not known. They're just not available for some of the more extreme conditions that we deal with in, for example, injected gas systems, which can be ultra high pressure, and we have to be aware of the limitations of the models. I wanted to slip in something about dense phase CO2, because this is a really hot topic for people. And at high pressures, of course, we get a change of CO2. When we're talking almost 100% CO2 here, we get a transition of a liquid phase at high pressure and a swap over into the gas phase here, and that's what's going on at these transition points depending upon the temperature. What we've got here is the water content. So the thing is that the liquid CO2 can actually dissolve a larger amount of water than the gaseous phase can carry. So if you have dense phase CO2, your major focus is on whether there are upset conditions that could lead to the dense phase generating some gas, because that will drop out water, and that water will be supersaturated with CO2 and very corrosive. So Mike and I published a paper along with other authors on this subject in 2010, and there's not been a great deal of advance in CO2 sequestration since then. So it's probably still quite relevant, the analysis we did at that point. Bear in mind that dense phase CO2 can have other impurities that are also very acidic, so you have to look out for those. And it's very, very difficult to monitor and to model this, and fundamentally the issue is that you've got to be looking more at process control. It's more about physical models than corrosion models. It's about controlling your water content here. Now I want to talk about the ways people misuse models, and that is common traps that people make. The oil industry has a peculiar use of the terms M and capital M, and double M and double M, and this is not understood in the same way outside of the oil industry. So people who come into this topic from universities often are bemused by the units, and I often do see factors of 1,000 wrong in flow rates that people put into software because they've misunderstood this. The pressures that we're using in the models are absolute pressures, and often the data we have is gauge pressures, so don't forget to add on an extra bar of pressure on the data. And we talk about mole percents and fractions in the gas phase often, whereas process engineering often gives these as fractions across all phases. So take care that you interpret the data you're given in the correct way, or ask for the right data. Flow rates are standard temperature and pressure conditions, whereas process engineering data can often be at the actual conditions. Huge difference there, huge difference. So, you know, again, ask for the right input data. And think about the source of the data. You know, people are not often collecting data for the benefit of the corrosion engineers. They're collecting it for sizing equipment or for reservoir engineering, planning, and all sorts of other reasons. So key data that we need for corrosion are overlooked. You know, some data is very badly collected, and some of it we really need to care about and some of it we don't need to care about. Flow rates are generally accurate enough, but acid gases, we have to be very careful about how they're sampled. They do have to be ideally sampled in pressurized bottles, not plastic bottles, and they, you know, the actual analysis of them in laboratories has to be done with care. Water analysis is another area. We often get pH values given with water analyses. Always just ignore them, because they are taken with, as we show on the right here, you know, the gas depressurizes out of the water, and so the pH values you read are always too high, and if you leave the model to do its calculation of pH, it will calculate the in situ pH, which is a much lower value because it's taking into account those acid gases. Now, process data is often very precise, but the ppm levels they give might not have enough significant figures to see ppms of H2S, and that can be very important. You know, you have to question whether there's water in lines that they say are water-free. And you have to bear in mind that salt carryover is not covered by process engineering, and we often get the issue about when we're selecting particularly CRAs, do we have a chloride concentration in this water or do we not? Is it salt-free? How much is that carried through in droplets through a plant, for instance? So you need to be always challenging the input data you've got, and often we ask people to send us their input data if they're having struggles with the output of a model, because our understanding of the input data from all the years of doing this modelling is often, you know, a few hints, and it helps people to get it right in future. The other thing is that you'll often get many operating cases provided to you as a corrosion engineer, and then you've got to question, you know, you've searched through these, you know, different summer and winter conditions and different years, and you pick which one you're going to actually model. And the service conditions can be very varying, and you have to think, are these extreme conditions really realistic, or what should you be doing? Now, we always say that corrosion is a gradual process. You're looking for the typical conditions to get the wall thickness loss over time. Transient extreme conditions for a few weeks, even a couple of months, are not going to massively affect the integrity of the equipment over its lifetime. But it's worth looking at a few sensitivity cases. But if you think about cracking can literally happen within a matter of hours or days. So you do need to look at those extreme conditions when you're picking alloys or considering other cracking mechanisms. Take care with the design pressures. These are for the mechanical design. You need to be working mostly with operating pressures. The maximum operating pressure for cracking is relevant. Don't be too negative. Don't pick the worst conditions and end up with something that you can't afford to build. People are always interested in modelling of the results. Mike published a paper on ECE modelling on the Bangora wells in Pakistan, and the reason I draw your attention to this is that we had data coming in year after year after year on these wells, and we were able to show a real consistency and understanding of what was going on in those wells, and really help the operator of the time to select the right approach for continuation. They wanted to delay tubing installation, and we were able to give them confidence to run through another 6 months, and then they'd run another log and check it and so forth. On the left-hand side, there was a paper published in 2006 by Rolf Nyberg. It has tests of a number of models, which at the time included the ECE model and various others, Predict and several others. They're not identified, but he tested a number of data sets against all the models. We were always very critical of this paper because he didn't have all the inputs that all of the different models needed, and yet they all got judged against these data sets. But we have picked out from that paper about 8 data where we could actually utilize the information, and we've got a reasonable prediction, and the ECE was also a pretty close match to these. So where are the gaps in all of this modelling? I've talked about the top line in sour service conditions, talked about the challenges of dense phase CO2. There are other oil field environments to be considered. Some of the refinery environments could be given consideration, where there are other additives in the streams to control the local pH and things like that, and some higher temperature conditions that are not adequately covered by the current models. And then we've got the stagnant dead legs and all the other challenges that where we move not necessarily the environment, but we move to a different mechanism. And, you know, how do we get people to realize that CO2 corrosion is only part of the story, and there are other mechanisms out there? So there's a number of gaps to be addressed. I'm going to pause for any questions on this now.
Okay, before we continue with question and answer, you have been talking quite a lot, so do you want something to drink first?
I'll take a drink whilst you're asking some questions. Yes.
Okay, it's very interesting session. So a lot of it's related to the quality of data and input data and how we use that data. A lot of, in my experience, a lot of companies just let the piping engineers put in the data, let the mechanical engineers put the data. So it's a garbage in and garbage out case. So let's go to the question. There are some questions that already answered during the presentation. So there is a one from Andre Diaz. Is there any heavy dependency on or influence of flow velocity with the pitting rate? So is the flow velocity is major driver to conclude pitting initiation or the rate?
That's a good question, actually. The pitting rate will be affected by the flow velocity because it's influenced by the CO2 corrosion rate, which is itself influenced by the velocity. So yes, pitting rate would be. Perhaps what you're interested in also is the velocity affecting the likelihood of pitting. Now, in actual fact, we have seen a greater tendency for pitting. I'm thinking of sour systems here. The slowest, stagnant conditions are areas where we can see pitting, and that's related to the stability of these sulfide films in the low pH conditions that can build up in stagnant areas and stagnant systems, and that can, I think, destabilize the sulfide film and give rise to a pitting attack. So I think that higher velocities are actually better at maintaining a good adherent film. Obviously, when you get to erosional velocities, if you get really high velocities, then you may strip that film, and that's a problem. But within the normal velocities we deal with, I think it's the low velocity end that's the problem for pitting.
Okay, thanks. That's a quite clear answer. So we go to question from other questions. So let's see. Is this model still valid in environment with extremely high H2S contents with elemental sulfur, or when there is some oxygen inside?
We have looked at systems with very, very high levels of H2S. I think some of the highest we've looked at have had even 40% of H2S in, and we think the model is still relevant at those conditions. There would come a point, I suppose, when if you go to ultra high levels of H2S, where you might enter into a dense phase situation, same as the CO2. It's not something I have got a graph of to study, but there could be that sort of end. But we think that within the practical systems we've seen, yes, we can cope with high H2S levels. Elemental sulfur is an interesting one. We do include elemental sulfur in our evaluation of corrosion-resistant alloys because that's part of the data that's available partly in ISO 15156, but also in a lot of test data that's been done. But for carbon steel, if we have elemental sulfur present, if it's actually in contact with the steel, it will cause very, very rapid pitting. We don't include it within the actual model, but if you had elemental sulfur present, you've basically got to think about either changing the material or managing that sulfur. If you can keep it in solution by putting a solvent in and keeping the sulfur in solution rather than as a solid on the surface, then there are basically corrosion management ways around it, but not corrosion modeling ways around it. So it's a problem. Oxygen is a classic one. We do get oxygen into our systems. We open and close them. We have shut-in periods. We have pig traps that we open and things like that. We really stress very strongly to our clients that they need to keep oxygen out of the system, especially if there's H2S present, because it can oxidize that H2S and give you sulfur in finely divided form, which is all very well, it flows along, but if it collects on the surface, then you would get attack of the steel there. So it's not one of the inputs in the model in that case either.
Okay, great explanation. Thanks a lot. Let's see if we have another relevant question to this section. Pak Kuku, how much time do we still have for this Q&A session?
I think we're okay for one more question. I think there was something about the materials, was there? I just wanted to perhaps go back to that.
Yeah, agree. Sorry? One more question is okay.
You were saying, can you please repeat what you're saying, Dr. Liane?
I think somebody, I'm going to jump in because I do know somebody asked about the 13, about the CRAs and whether we take into account chloride content. Well, as you see from the internal domain diagrams that I showed, we do consider the chloride content for all of those different alloys and how that affects the surface passivity, the stability of that chrome oxide film. But I think the question was geared at thinking about chloride stress corrosion cracking on the outside. And that's a really good point to bring up because no, the model is not thinking about that. So when we're saying 316, for example, would be a great material to use, we're all aware that there's a risk of chloride stress corrosion cracking on the outside of the material. And those of you who are experts in risk-based inspection RBI systems will know that we have to consider all these corrosion mechanisms, but we also have to consider everything that's going on the outside as well. So do we have CP? Do we have hydrogen embrittlement? Do we have chloride stress corrosion cracking? Have we got risk of brittle failure? Have we got fatigue? So always keep in mind that corrosion's only part of the story. In selecting materials, you've got to take a broader view outside of it and think about all of those other mechanisms as well. And a key part of setting up our RBI systems is understanding the corrosion rate. And at the beginning, you really need modelled corrosion rates for your systems because you've not got any inspection data to work from. So it's really good to incorporate corrosion modelling into setting up an RBI system. And it's very useful through the life of the system as well to validate some of the data you're using. So that's really my point, is that it's just part of the story. I'll move on.
Thank you. So we can continue with the simulation. This is what people have been waiting for.
Okay, right. 2 quick slides then. So first of all, to say that the Larkton CM model is, as we've explained, if you use the basic settings in it, then you'll get the same kind of results that you've seen in other models based on the CO2 Devard nomogram. But if you want to, you can use more advanced settings with Larkton CM, and I'll show you some of those. It's got really wonderful interface to work with, which I'll demonstrate shortly. And then it's got an option to use flow modeling, which is terrific, and a much expanded selection of materials. It copes really well with wells. We can put a full deviation survey in. We can handle bubble point behavior and different artificial lift systems, and it copes with elevation profiles in a very easy way. So I'm going to move on, and it's cloud hosted, so you can access it anywhere. You can access it on your phone. It's very fiddly, but you can really get to it wherever you're on the internet. There is an on-premise option for those of you who have businesses that require that. It's very secure. And you get great technical support. We don't have any data of yours on the cloud. That's the key thing to bear in mind. So I'm going to just click on here. This is the link to the actual software. And I'll expand my screen a bit here. And this is the input page, and I'll sign in. The first thing you have to do is accept the terms and conditions. And then you see the page. Now, I realise this is a little bit small. Let me see if I can make it a bit bigger. What I've got on the left here are a selection of input of files that I've been working on recently, or I can drag and drop files to here. So what I do want to do is to also...
Pak Kuku, you want to do some closing?
Yeah, I think before we close, let's take a picture together. You can activate the camera, and
let's have some more pictures. Yeah.
Large gallery. Oh no. Gallery. Yeah. Okay. Okay. Let's take the picture. Let me do it with. Okay.
Aku yang akan foto.
Oke, Suryani boleh fotoin deh.
Ya, makanya tadi aku tanyain sebentar together mode aja ya kita ya.
Oke.
Is it okay all? Ya, foto sebentar ya. Wait a minute. Oh, sorry.
Okay.
You're going to do it again. I'll take my glasses off. I can't see you.
Okay, cheese everybody. 1, 2, and cheese. Oh, ada yang admit sebentar ya. Wait a minute. Okay, another one. I think if I can change the background together mode, is there any option? Nggak ada. Udah together mode yang ini aja ya. Okay, another one. 1, 2, and cheese. Okay.
Thank you.
Thank you.
So yeah, we
Thank you
are
very much.
at the end. Yeah, thank you everyone, and we are at the end of the presentation, this session, and then thank you again for everybody who attend this technical group discussion, and also, of course, to Liane and Mike. Every success for you for the company. And
thank you.
Yeah.
From me and from Mike, we want to say thank you so much for the opportunity to speak to you all today, and I so much respect the fact that people have given up so much time, and thank you to you for organising it, Kuku. That's really great. Thank you very much indeed.
Yeah, it is teamwork, Liane.
Thank you, Liane, and thank you, the team. I think we should make it 3 hours. 2 hours is not enough. So anyway, for reminder for you that are located in Indonesia, if you want to know more about Lacton, you can see the screen. There is a contact number over there. Or for anyone reside outside Indonesia, you can go to Lacton website and fill the contact to Dr. Liane.
Sure. Thank you very much. Sure. Get in touch with our partners